Dear friends, this is my tutorial 12. So in this video I'm going to tell you how to do band structure calculation in VASP and analysis with VASPKIT. So this is the molecular structure of bilayer structure of molybdenum sulfide. This is the cell length I shown here 3.16 and the C size is 12.29 for Armstrong, and alpha beta gamma is 1990 120. The symmetry space group is P63, MMC is hexagonal. This international table number is 194. These are the important lattice parameters of this molybdenum sulfide 2H. So this is the paper they reported the experimental band gap of this molybdenum sulfide, showing that they mentioned that here you can see here 1.8 EV. So this reference 16 paper is this is the one. This paper also they mentioned is 1.8 something. So they quoted this paper for this Nature Nanotechnology. So we will calculate for this monolayer MOS2, and we'll compare with this experimental one. So there are several steps to do band structure. First step is prepare MOS2 postcard file. Then you need to standardize the MOS2 postcard. That means that for 2D materials, keep the center of Z coordinate of MOS2. So it should not be in the bottom or top, should be in that center of that Z axis. So this is the main thing. So we will do this with the VASPKIT tool. Then after preparing standardizing things, you need to do geometry optimization. Next, to do the single point energy calculation in order to get charge curve file. Then you make new folder and do your band calculation. I will tell you the in-car file parameter, other things, and we can do the post process of band structure. From there we will get our band gap and Fermi level and valence band, conduction band, and also everything we will get. So we will see first we will download our zip file for MOS2. Okay, so we will go to our corresponding folder first. So this is our folder. First, prepare MOS2 postcard. Okay, first we download. This is already I downloaded one of the postcard. So I will tell you where I downloaded. So if you see, this is that I downloaded from the CCDC database. So the database code ICSD number is 49801. Just you can, if you have any kind of this ICSD number, just go to CCDC. So just go to ccdc.cam.ac.uk. So now you can modify. So you can see identifier. You can just paste your that CCDC number, ICSD number. You can also click. If you click this, you will get from the ICSD only, not from CSD any other database. So just you can. Just you type this one and give search. So this is our ICSD number. So this is our crystal structure 2H MOS2 bilayer structure. So we can download this from current entry. So that will have something like this. Just you can mention your name and email ID and something, and click download. That's all. So it's downloaded this is the zip file. We can copy this. So these are the same number I already downloaded, but I just want to show how to get that MOS2. I am showing this one. So now we have to make our monolayer of molybdenum sulfide. So for that we need to open that Material Studio. So just drag this here. So display option, I already saved is a white background, so we can change it into black. So go to the display option and display style, make it ball and stick. If you want to connect with the bond, you can click this one, it will connect. So this is our molybdenum sulfide bilayer bulk unit cell. So here we are going to make monolayer of MOS2. For that, just go here, build, symmetry, supercell. You can click, or you can just do, then only the phase group will change. Otherwise, if you delete this one, everything will go. If you delete top layer, it won't go. So you can delete the top layer, select the top layer, select and remove. So our monolayer is present still. Okay. So now we need to adjust our crystal structure. So rebuild the crystals. Go to, now you see is changed actually from the initial space group. So you can go to lattice parameter. So here you can give 15s in order to avoid that interlayer interaction. So just give 15 Armstrong C, the C length. So apply, it will increase. That's all. Now you can save as a zip file. So layer MOS2. Okay, so we have generated monolayer. So this is our monolayer S2 already saved. So we need to change into postcard file. For that, just you can open with Vista. So you can see your postcard file, zip file here. Just save as export data postcard. Type postcard file, it will save as a postcard. So now we have downloaded and made a monolayer, and we also created the postcard file. So now we have to do the standardization. Okay, so already I told you in the PowerPoint slide standardization. So for that, what we have to do, so we need to standardize the things. Just drop our created postcard here. So copy, so go to corresponding directory. So our postcard is there. Now you can type VASPKIT. So you can see here 2D material kit, you type 92. So standardize 2D crystal. You can also use this 921, 923. So we can use 923. So that's all. So our new postcard is written. So this is the postcard underscore RGB file. So just we'll go there. We can find our postcard. This is the standardized postcard. So I will show you this postcard, how it looks. So this is our first postcard file. This is standardized one. So you see, this is the MOS2 is to move to the center of the z-axis. Okay, this is very important. Without don't do like you have to do these things. So that's so using this postcard file, you can convert into, you can also see how it looks here. So this is the MO1, S1, S2. This is the parameter. This is the lattice 3.16. Okay, so you use this postcard file, do first geometry optimization and single point energy calculation. Regularly, how you are doing your single point energy calculation or geometry optimization, do same things. There is no changes. So I already completed that geometry optimization and SEF calculation also. So I will show you the optimization input file. So this is the optimized folder of MOS2 monolayer. So I will show you the incar file. So you see the incar file here. So I want to tell you one important things here. So actually I'm doing here that I spin 1. That means non-spin polarized, and LS orbit also turned off because I'm not considering the spin orbit coupling and the spin polarization. Okay, that's why because of that I did not turn on the L orbit 11, and I spin turned put into 1. Okay, and that's all. The maximum also default it won't run. So that also I just put in the hashtag here, that it won't read the incar file. So other parameters are same as the like geometry optimization. There is no change. Okay, you carefully check. If you want to do spin polarized also, you can do it. This is up to you. There is no problem. So I'm doing here non-polarized and without spin orbit coupling. So this is the incar file. So this is optimized concar. So this is optimized MOS2 concar file. So after completing the geometry optimization, so just to do it for single point energy calculation. So I made it, you take that concar file and make it the single point energy calculation. So this is the single point SEF calculation folder. So just I will show you that incar file here. So here you see there is no change here also. Just you need to turn on that L wave and L charge in order to get charge car file, and then you put Ibron -1 for single point energy calculation, NSW 0. The default I spin 1. So default and maximum also we need to put that we need to turn off. This also we need to turn off. That's all. There is no change at all here. Just use this incar file for your SEF calculation. So K point, I did not mention this. I am using the gamma point 1212 K point for optimization and also the SEF and SEF calculations. Okay, so this is the important things. After completion of this single point energy calculation, you will get charge car file. So this is the very important for your band structure calculation. So I will show you here that folder itself. So here only I did the graphene also. I will show you the MOS2. This is the SEF calculation. So this is the completed things. So you can also view here. So the writing the wave function is calculation completed, this one. So So now we have to make a file for the band structure calculation. That is very important. For that part we have to do. So just I want to show you what are the files required from that SF calculation folder. So here we need some important file like port car, so charge car, and the script file, and post car. I think I deleted. Yeah, post car is there. So this important 4 file we need for our calculation. So some kpath file we need to generate. I will tell you that next. So first we will copy these files to our folder. So copy that, change directory, not here I think. So we need to copy from here. So just copy this line. So just cp port car, so we can see our file cp port car. So then we need this summation script. Then so port car kpoint file no need. So we copied charge car. So these are the 4 important files to copy to that band. Just copy, paste. So maybe our files are copied from that SEF to this folder. So these are the some important file. So here we have to make 2k path line 2k path kpoint line files. So just copy this, cd, go to that folder, you can run VASPKIT. Then run VASPKIT, then run 302. So this like that it will read, it will show your structure type and lattice constants and input the lattice angles and previous lattice and other space group, everything. So here we are using our P1 structure, but that's why it's not showing that exact face group and that's everything. So if you use the bulk structure with the same face group, that will show reflect everything here. Okay, so because of we are using mono layer, that's why it did not show exact unit face group. So here so kpoint file is written here. So this is the kpoint file. So just we can refresh. So see some new files are created, but we don't want this in car. Just I will delete it. So this is the kpath file. You can open and see. So this is the kpath gamma mk gamma. This is the kpoint file generated by VASPKIT. We need this kpoint file for our band structure calculation. So now what you have to do, you can copy kpath dot into kpoint, cp kpath dot into kpoints. Okay, so this is the our key point. You can highlight this is x, it won't read, just you can mention like this. We have a key point, port car, post car, charge car, submission script. So we need incur file. I already created incur file for that one, so I will show you that incur file for band structure calculation. So this is the incur file for band. So I mentioned here title also, you can see. So here also you need to turn on L wave L charge true. So here important things is you need to mention I charge 11. Okay, this is the important. So other things are single pentagon I brown -1 and also NSW 0, that also same, there is no change. So that's all, there is no change here. Here also I spin 1, we are doing that I spin non-polarized one. So other things are same only. So and also you can also here you need to turn on LR bit 11. Okay, LR bit 11, this is for the band calculation, this is very important. And then you also mention NE DOS 1000, this is enough. So how many point, this one, and LR bit 2 and I charge 11, these are the important parameter for DOS band calculation. You can, I will share this input output all files to you. You can also try it yourself. You can also follow these incur files to do your band structure calculation. So that's all. So just we can copy this in incur file here. So we have incur, k point, port car, and submission script, post car, and a charge car. So that's all. These are the important files you need for the band structure calculation. Just you can submit this calculation. You can copy this, go to and submit. Submit, that's all. So actually I already did this calculation. So now after completion of calculation, we need to do some post processing in order to get our band structures. Okay, so this is the one already completed. Okay, already completed. Now I will show you how to get your band structure after completion of the calculation. So here just copy this path. So you can type here VASPKIT. So here you can see 21 is the band structure. 21. So here you can see 211 on the band structure analysis. 211. That's all. So here, so everything is okay. There's a reading k path files and return k labels files, and also band dat and a reformatted band. These are some uses is there. You can see yourself and find, and return k lines file, and this is the band gap file. These are the important files. After post processing the things, it will generate it. So if you refresh, you will see all the files. So these are the recently generated files. Okay. So these are the important file. So now we can so I will show you that band gap here. If you open this band underscore gap with notepad plus plus, so you can find this the band character is direct. Band character is, it will, I will show you direct, and the band gap is 1.75. so already showed that band gap of monolar experimental is 1.8. so here we are getting us near to 1.8, so 1.75, so is, but we are close to that experimental level. So these are the BBM and valence bond minimum, connex bond minimum, West Fermi energy. This is HOMO LUMO. So this is a location of a VBM and the CBM. So here important things is you can get the band character and band gap. So this is the very important things. Okay. Then you can K labels. So this is very important in order to plot the figure in the origin. So while plotting, you can, I will show you the uses. This one, this is a K lines that this I think no need. So that's how we will plot in our band structure now. So this is the band dat file. Band.dat means data file. Okay, just you can open. So these are the, just to drag and open, just to select this one, plot. So this is the things. So here is the y-axis is very large, so we can also short. So we can make 4. I think this is enough. And that, okay, so this is the band structure of this one. So here you can see here that we need to cut up to here. So for that, what already I told you, we need to see our K labels. So this is the K labels. So the first here is the gamma, and here I will see the M. Here you can see that K, here the gamma. So 3.316 we need to cut 3.316. so just you can make it 0 to 3.316. so is everything okay? So you can also make it grids. So we made it the grid. So we can also put it here, increment 1. So on 0 to 4, 0 to 4 we have mentioned. Okay, so now we need to mark this line, this MK line. So that means in here you can see the line 0.2 you can mention, then you can very clearly see. So M point is 1.15 around. Okay, so just to make it 1.2, this is 1.15 maybe here. Okay, 1.1 here. So one more things, 1.8. So you can also, I think, make it somewhat good to black thick line. So you can also change into line somewhat thick too. I always use 2. So you can remove this, I think no need of hereafter. So you can also remove this tips. bottom text out is there, just to put none. Here also none. I think this no need. So this also. So this also no need. So here you can arrange. This is energy electron volt. So here also you can make it bold 22. This looks good. Then you can make it that a gamma symbols. So go to text, just to keep here symbol map. You can insert a gamma. So that's all. This is our things. So our band gap is 1.775, 1.75, 1.76. Okay. So maybe our band gap is here will direct band gap. So yeah, our band structure calculation completed. Just you can save it. Yeah. Save. So our band structure calculation is completed. Likewise, you can do your 2D materials like graphene or any other material, phosphorine or boron nitride, whatever you want to do, you can follow this method. You will get exact band structures. So thank you for watching. If you like my content, please like, subscribe, comment and share, and also share to your friends. So please click the bell icon, so then only you will get my next update video. So thank you for watching. Thank you so much for your valuable time. So I will share this all the files to the download link. You can download it and use it. Thank you.